I just want to go through a summary of all the inference procedures that we have used so far for proportions and means, both 1 and 2 sample. First of all, I want to recall the definition of a sampling distribution. A sampling distribution is the distribution of sample statistics from all possible samples of size n from the same population. Let's consider a population that has a proportion p and a sample proportion p hat. Let's look at the sampling distribution of p hat. If I were to take all possible samples of size n from this population and calculate the proportion of successes, whatever I considered a success to be in that case, maybe number of red beads, for example, I would find that if they were random samples or collected due to random assignment in an experiment, that the center of all of the p hats would be p, the true population proportion. That the standard deviation for p hat would be the square root of pq over n, if n is less than 10% of the population, if I'm sampling without replacement. And I would find that the shape of all my sample p hats would be approximately normal as long as np and nq are greater than or equal to 10. We have done simulations involving this and found that we didn't do a complete sampling distribution because that would require taking all possible samples of size n, but we would take a large number of samples of size n, and we saw that approximately normal shape. We saw that the center and spread were as we expected using these formulas here. So based on that sampling distribution of p hat, then we have a pretty good idea of what to expect my samples statistics to look like from a given population, what my sample proportions would look like. So based on that, then we do some inference. So we can do a confidence interval. Remember, a confidence interval, I'm not taking all possible samples. I'm just taking one sample using one p hat to estimate p. So I have to create a margin of error around it because I know that p hat can vary from sample to sample. So my margin of error is based on this standard deviation that I got here. But I don't know the population p, so I have to use the sample p hat to compute what's called the standard error of the statistic. So p hat plus or minus a z critical value times the standard error of p hat. To check my large enough condition here, I have to use np hat and nq hat. That looks like a p hat. It should be np hat and nq hat because I don't know p. Now for a hypothesis test, we're looking for evidence that the true population proportion p is greater than, less than, or different than some hypothesized value for p. So my null hypothesis has some given value for the proportions, say 0.2. That would be my p naught, or my hypothesized value for p. Using one sample p hat, I create a test statistic. I see how far that p hat is from my hypothesized value of p, divide that by the standard deviation, and that tells me how many standard deviations p hat is from p naught, and I see how unusually far that is. Notice that I do not use p hat and q hat here. I use p naught and q naught, my hypothesized value of p for the standard deviation, because I am assuming, for the sake of rejecting it, that this is the true value of p. This is what I'm basing my population on until I prove otherwise, or until I get evidence for something else. And then once we find the test statistic, we calculate the p-value. If p-value is low, we reject HO. When we check conditions, we check using p naught and q naught, because that is our assumption of truth at this point before we run the test. Now with two populations, we're looking at the difference now in two populations. And we did this with two samples of red beads, 40% and 20%. And we took multiple samples, we found their differences, and we plotted the difference of p hat and q hat, and we got at least a partial sampling distribution of p hat 1 minus p hat 2. We found that the center was as expected, very close to and it would be exactly, if we got all possible samples, is P1 minus P2. Now the spread is based on random variable studies that we did in Chapter 6. Recall, if we had two random variables, x and y, if we subtracted them, the expected difference was just the mean of x minus the mean of y. Mean and expected value mean the same thing. But the standard deviation was not this difference of the standard deviation. In fact, we don't ever subtract the standard deviations at all because we have two sources of variability now. One source of variability when we sample from X, from the population X, the other from the second population. So we actually increase our variability, but we don't add the standard deviations either. We add the variances, or the standard deviation squared of both variables. So notice the standard deviation looks like this, square root of PQ over N. If we square that, we just get PQ over N without the square root sign. So this is standard deviation squared for population 1, standard deviation squared for population 2. We add those together, take the square root. That is the standard deviation of the difference in the two population proportions. Once again, the shape would be approximately normal, assuming all of the conditions are met. So random condition, 10% condition, NP and NQ both greater than or equal to 10. Make sure that you check separately, check the conditions for each population. Now when we do the confidence interval, then we have the very same standard deviation that we saw here, except that we're using our sample p hat and q hat because we do not know the population, because that's what we're trying to estimate. For a hypothesis test, though, we have a special situation. Our null hypothesis value for the difference in proportions is 0. So we can't use our null hypothesis difference to create a standard deviation, because then this would be 0 here, and we would have a standard deviation of 0, which is clearly not true. So we have to have some other way to come up with a standard deviation for our hypothesized population difference. So we do what's called a combined or pooled p hat. So p hat c means p hat combined, or you could have, I guess, p hat p for p hat pooled. But anyway, you add together the two sample successes, so the number of successes you got for each from each sample, and the two total sample values. Basically, you combine them together to get one sample proportion by putting the two samples together. And the reason we do that is because our hypothesis is that there is no difference between the two population proportions. So if that is our hypothesis, then it only makes sense to combine the samples together, since there's no difference between them for our hypothesis, okay? And that's what our hypothesis, our model is based on, there is no difference. So we take the observed difference minus 0, our hypothesized difference, divided by the standard deviation, in which we use p hat and q hat combined for both numerators here, but the two different sample sizes. On the formula sheet, it's just written like this, where the p and the q here are the p and q pooled. Okay. Now, we typically use, so this is going back to the hypothesis, we typically use the p hat 1 and the p hat 2 to check the large enough condition, just like we do for the confidence interval. But if for some reason one of those values was less than 10, then try the condition again using the p hat, q hat combined for both samples. Often that will do the trick if this one didn't work. All right, let's take a look then now at our, actually I think I'll stop the video and we'll do a separate video then for the two t-tests. No, I'll just keep going because this isn't going to take that much longer. A lot of this is repetition. So now let's say we're doing population mean. So we have population mean mu, sample mean x bar. And let's assume too we also know the population standard deviation sigma. So we see that mu of x bar is just mu, the mean of the population. Sigma of x bar is sigma divided by the square root of n. This is assuming that the random condition is met for the center, the 10% for the spread. The shape is approximately normal if sigma is known, okay, if population is approximately normal, and if the sample size is greater than or equal to 30, or one of those two is true. But remember, for inference, we just have only one sample. So if the population is, if we don't know what the population shape is, and if we don't have a sample greater than or equal to 30, that's when we would make a graph of the sample and check for skew or outliers. Now, usually the population standard deviation is not known if we're doing inference. If it is, we can use a normal model. We can use Z instead of T. But if sigma is unknown, we go to our T procedures, which allows for a little extra variability to compensate for the fact that we don't know what sigma is, because S is generally less than sigma. Our sample standard deviation won't have as much variability in it as the entire population would have. So for the confidence interval, we have our sample statistic, x bar plus or minus our t critical value, and t critical value is based on a certain degree of freedom, which is n minus 1, sample size minus 1. And then, of course, we have to use our sample standard deviation divided by the square root of n. For our hypothesis test, same thing. We use our hypothesized mean value. We see the difference between our observed sample mean, our hypothesized mean, divided by the standard deviation. Once again, since we don't know sigma, we have to use S for our hypothesis test too. If sigma was known, then this would switch to a Z critical value instead of T critical value. Once we get our T critical value and our P value, then we can finish running the test. So those are the important formulas here. Now, if we have two samples that are paired data, not independent, okay, if they are not independent, then we cannot do what we do down here, which is adding variances. We have to have independent variables to add variances. So if the two samples are not independent of each other, we need to find the difference of each pair and then do a one sample t-interval or t-test of the mean difference. So basically we're doing the same procedure for a t-test, but we just take the differences of the pairs first. But what if the two samples are independent of each other? Then we are dealing with two population means, x bar, mu1 and mu2, and two sample means, x bar 1 and x bar 2. So this is the mean of the differences, and this would be the difference of the means. And you have to be careful how you say that, the mean of the differences or the difference of the means. So here we have the, if we were to do all possible samples of the same size, same sizes, okay, like x bar 1 would all be the same size, x bar 2 would all be the same size, subtract the means. Notice these two sample N1 and N2 don't have to be the same as each other, but they have to be all the same in a sampling distribution for all x1s and all x2s. X1s would all have to be the same as each other, and X2s would all have to be the same as each other, is what I'm trying to say. Probably did not need to say that, so you probably got it by now. Okay, so the mean of the differences, the mean of all the differences of the sample mean should be the differences of the population mean. The standard deviation is based on adding variances. So here we have sigma divided by the square root of n. If we square that, it's going to be sigma squared over n. Sigma squared over n for both samples. Add those together, take the square root of that. The conditions are the same and must be checked separately for each group, the same as for one sample. But there is a fourth condition. The samples must be independent. So we only use two sample procedures if the samples are independent of each other. No paired data allowed, because if they are not independent, then we cannot add variances. Not a whole lot different here, except for the degree of freedom. The degree of freedom is a weird number here. Here we have x bar 1 minus x bar 2 plus or minus t critical value, and here's the standard deviation based on adding variances and using sample standard deviations. We do the same thing over here for the hypothesis test. If the sigmas were known, we could use Z, and we'd have sigmas in here. But usually it's not. We're looking for our hypothesized, whether our mu1 minus mu2 is greater than 0. We don't have to do any kind of pooling here. You don't pool with means, just with the proportions. So the thing about the weird degree of freedom, they tell you a couple ways to calculate that in the book. but don't worry about either one of those. Just write down the number you get on the calculator. So if you look at there is a video where I go through the calculator procedures on the Nspire for these two example problems. And these are the two examples I would suggest for a 2-sample t interval and a 2-sample t test, these two examples in the book. So look for my calculator instructions video, and that will explain how to handle that weird degree of freedom. All you do is write it down basically. It'll show you how to deal with entering the data, entering the appropriate values using either data or statistics, one of each example, and an interval and a test. So this is a fast but hopefully thorough review of all the different inference procedures we've done up to this point. We'll have a couple more in chapters 11 and 12 to deal with, but the logic of the confidence interval and hypothesis test will be the same for everything.